Good day, everyone. I'm sure you noticed that when we submerge in water, it seems that our weight in water is less than the weight in air. So, meaning, if for example we have a stone, then we want to measure the weight of the stone, so we need the weighing scale. The reading on the scale is actually the weight of the stone, and that weight of the stone is actually the weight of the stone in air. So we have the reading on that. But take note, we observe that when we submerge the stone to any liquid, the weight measured from the weighing scale is now different compared to the other. So, for example, suppose we have the alcohol and we submerge the stone on the alcohol, then we come up with a reading. So it was decreased, meaning the amount of force exerted on the string, which is the weight of the stone, is now decreases. Meaning the weight of the stone in air is this small compared to the weight of the stone in air. Okay, so if we have another liquid, let us say water, then we have another weight. So meaning different fluids have different weight. So if we have this seawater, we have another weight. Okay, so that's it. Meaning different fluids have different weight of the stone when we submerge. So we have the air, the alcohol, water, and seawater. All of them are fluids. So the question now is why? Why it happens? Why is it that the weight of the material is different on different fluid? So actually the answer is because of the buoyant force. So in this video, let us study on how to calculate the amount of the buoyant force exerted on any of the fluid. Okay, so we will study buoyancy and the Archimedes principle, because the buoyant force is derived from the Archimedes principle. Okay, so let's start. Now, look at the figure. We have the word eureka, and that eureka is very familiar on us during our high school days, because the meaning of eureka means I found it. Archimedes found out that the volume of his body submerged in the tub should have the same volume of the water displaced from the tub. So when he saw the displaced water from the tub, he inspired after seeing. Then he shouted the word eureka, means I found it. Meaning he can compute any volume, irregular volume, by displacement process. So he will submerge it, then obtain the displacement, because that displacement is the same volume as the volume displaced. So that's the meaning of eureka. Now from there, the Archimedes principle was born. Okay, so by statement, according to Archimedes, that any body immersed in a fluid is subjected by a buoyant force. In simple bisabnat, meaning any particle, submerge it to the fluid, gas or liquid, all of them will be exerted by a buoyant force. The direction is upward. It is vertically upward. And that buoyant force is equal to the weight of the fluid displaced. Meaning, the displaced fluid from the tub of Archimedes is actually, the weight of that is actually the buoyant force. Remember that the volume of the submerged is the same as the volume displaced. Another thing is the volume, the weight of the displaced fluid is equivalent to the buoyant force. This is Archimedes principle. Okay, so for example, we have the container, and the container contains fluid, and we have at the level of the fluid, we have the outlet overflow pipe. So we place another container in order to collect for the overflow, meaning any particle submerged on that surface, the overflow will be collected, no, from the outlet towards the container. Okay, so notice that it starts to overflow, then the buoyant force increases, and the maximum buoyant force will be when the particle is fully submerged, and the flow will stop on that level. What does it mean? It means to say, according to the principle of Archimedes, that the volume of the submerged particle, the stone, the volume of the stone is the same as the volume of the fluid displaced, and it was being collected in the opposite side. So the fluid displaced weight also. The weight of the fluid displaced is the same as the weight of the buoyant force, and that's according to principle. And the buoyant force is what? Directly upward. Okay? So according to the Archimedes principle, that any body immersed in a fluid is always subjected by that force. Remember, force is upward, and the amount of force, take note, is the same as the weight of the fluid displaced. Meaning, if you measure the weight of the fluid displaced, that weight is the same as the buoyant force. Meaning, the greater the weight, the greater the buoyant force. Meaning, the greater the volume of the displaced, the greater the buoyant force. Another thing, the greater the density of that fluid, the greater the buoyant force. Why? Because the weight is directly proportional to the volume and its density. We noticed that in our previous video. Now the question is, how to compute the weight of the fluid? Because we badly need the weight of the fluid, because that weight fluid displaced is the equivalent to the buoyant force. Okay, so take note, in our previous video we learned that the density is mass over volume. If we multiply it by gravitational acceleration, the mass times g is equivalent to the weight, which means that rho g is equal to W over V. V is the volume. So take the diagonal product, then we can say that the weight of any substance, remember, regardless solid, gas, or liquid, the weight of that substance is equivalent to rho GV. Rho means the density, mass density, times the acceleration due to gravity, multiplied by its volume, corresponding volume. That's it, no? And this formula is very helpful if we are calculating the weight of the liquid or the fluid. Okay? Why? Because all you need to do is to multiply its density times the gravity times its volume. For example, I want to know what is the weight of the water in, for example, the water is 0.5 kilogram, 1/2 kilogram of water. What must be the weight of that? How many newtons are there? Okay, so all you need to do is to calculate using that formula, rho GV. Rho is the density of water, and the density of water is 1000 kilogram per cubic meter, as we learned in our previous video. And G is 9.81, the Earth's gravitational acceleration, and the volume is 0.5 kilogram. So multiplying the three, the 1000, 9.81 times 0.5, and take note the unit is in Newton because volume can be cancelled out, and the kilogram meter per second squared is Newton. So calculating the values, we result 4,905 cubic meter. That is the weight of the, no, that's Newton, sorry. It should be Newton, 4,905 Newton. Kindly remove the cubic meter, replace it with Newton. So that's the weight of the water, the 0.5 cubic meter is 4,905 newtons. Okay? So going back to the question mark. How to compute the weight of fluid displaced? We need that because that weight is the same as the buoyant force. So using this formula for the weight, the buoyant force now is the same as the density of the fluid, take note, the fluid displaced, multiplied by the gravitational acceleration, multiplied by the volume displaced. So in order to compute the buoyant force, we need the volume displaced. So measure the volume of the displaced fluid, then multiply it by the mass density of that fluid, not in the stone, remember, it is the fluid. Then multiply it by the Earth's gravitational acceleration, and that will be the buoyant force formula. And that is according to Archimedes principle. Which means that when the particle is in fluid, then there is a buoyant force. Now, not only in liquid, in gas also, there must be a buoyant force because the air should have the density. So, rho g v. Okay? But remember that the density of air is a very, very small, then the buoyant force is present, but it is negligible. So, usually, we don't need, in our previous topic in dynamics of motion, we did not involve the buoyancy. Why? Because we studied all particles in solids, not in liquid and gas. But in fluids, buoyant force is significant. Okay? So, again, anybody immersed in a fluid is always subjected by a buoyant force. And that force is directly upward. And that force is equal to the weight of the fluid displaced. Okay? Another thing is the volume of the stone, take note, which is submerged into the fluid. The volume of that is the same as the volume of the fluid displaced. We call this as displacement process. If you don't know the weight of the stone, the volume of the weight of the stone, then measure the weight of the displaced fluid, and they have the same value. Okay, so meaning, if I want to measure the volume of the stone, I will place it, submerge it into the graduated cylinder. Then the increase of level, measure the increase of level of the water, the increase of the level of water, the height of the water. Okay, in ml, then it should be the volume of the fluid. Because the volume of the submerged is equal to the volume displaced. Archimedes principle. Very clear. Okay. So in order to apply the principle of Archimedes, let us have this problem. The problem says that a slab of ice floats into the freeze lake. So meaning we have the lake. Now take note that the lake is what? The density is 1,000 because it is a freshwater lake. 1,000 kilogram per cubic meter. It's already given. Now the question says that what minimum volume, okay, must the slab have? Meaning, what's the volume of the ice? For a 65 woman, okay, on top of that ice, okay, the 65 woman on top of that ice, without getting her feet wet, what is the volume? Okay, take note that the weight or the mass of the woman is 65 in kilograms. Pero if you call it as weight, it is kilogram, 65 kilogram force. So the question says, what is the minimum volume? Minimum because it can be more than. When it is more than, then partially of the ice was submerged. If you increase again the volume of that, then it increase its floating distance. But if you call it as a minimum volume, then the ice is completely submerged without getting her feet wet, the woman. So how will you deal with this problem? You are asked what is the volume of the ice. Remember, the ice will float into the water. Why? Because in our previous video in density, remember, that the smaller the density, that particle will be on top of the greater density. That's why, again, we say that the oil will float into the water because oil has less density, while the stone will submerge. Why? Because it has a greater density, or the specific relative, or the specific gravity of the stone is greater compared to water. Okay? And the oil have a less specific gravity compared to air, to water. That's why it floats into the water. It is actually, it is not the weight. Again, it is the density. The ship floats into the water. We learned that in the previous video. Why? Because the density of ship is less than compared to what? Compared to the water. But the needle submerges because the density of the needle is greater compared to the water. Okay? Now, take note that we can explain that in terms of buoyancy. The ship will float. Why? Because it has a greater buoyant force. And that buoyant force is actually greater because of the greater volume displaced. The ship has a large displaced volume, then it has a large amount of force applied upward, and that's the buoyant force. Okay, so the question is how to solve this problem, how to compute the volume. Okay, now remember that when we say that the ice is actually at the top layer of the ice is on the level of the water, meaning it is completely submerged, then the system, the ice should be in at rest, and also the woman on top should be in at rest position. It will not go down, it will not go up. So the feet of the woman is approximately at the level of the surface of the water. So it should be static equilibrium, meaning we can apply the principle of Newton. The first law of Newton says, if you sum up all forces, the sum should be zero. If the net external force is zero to the system, the body is at rest. Or a body will continue in motion without stopping if the net external force is zero. So in this case, the net external force is zero. So how to solve this? Identify all the forces on the system, the body, the woman, and the ice, because it is considered as one system. So meaning you have to identify all the forces. What are the forces on that? Okay, take note that in our previous videos in Newton's law, we need to construct the primary diagram, and the mass of the woman actually produces weight. Okay, so one force of that is the weight, but the mass is kilogram. So we multiply it with the gravity and acceleration 9.81, and the answer should be 637.65 newtons. That is the weight now of the woman. Okay, so it should be downward because it is the force that the earth exerts on the woman. So the weight, our weight, is always downward towards the radius of the earth. That is one force on the system. Another is ice has a mass. So there must be a weight downward. Okay? We don't know what's the value of that because you are asked what is the volume of the ice. So in the problem, it was not given, but remember that the weight of ice exists on that activity. So there are, for now, we have two forces, and all forces should be downward. Okay? So because all forces is downward, and take note that the woman and the ice is at the level or static condition, meaning the upper part of the ice is on the level, on the surface of the water, then there must be a force that counters the weight of the woman and the ice. And that is what? Buoyant force. So the force that tend to move up to balance the two should be the buoyant force. No other force on that. And that is only the buoyant force. Meaning, in that case, that the buoyant force exerted the force by the woman, which is his mass, her weight, and also the weight of the ice. Why? Because the system is in equilibrium, balance. Okay. Now, in order to apply, remember in our previous topic in Newton's law, that in order to provide or apply the Newton's law, you need to overlay the Cartesian coordinate system. So we will assign the Cartesian. Now, in our assumption that upward forces must be positive, downward must be negative, and forces along x, to the right positive, to the left is negative. But in this case, nothing to worry with respect to x, because although we have forces along x, in this case, the forces on the side of the ice, the hydrostatic force, it balance with another force on the opposite side. So nothing to worry, the force on the horizontal, because it was neutralized by the fluid pressures, forces on that side. So we will focus on the y-axis only. So in that case, because we orient the Cartesian coordinate system, then all forces must be downward and all forces must be upward. So in that case, the weight should be downward, the woman, and the weight of the ice should be downward, negative, but the weight of the buoyant force should be positive because it is directed upward. So this is it, no? So there are only three forces. Okay, so then apply the first law. The sum should be 0. So consider only the upward forces and downward. So then we have the buoyant force as positive, the weight of the woman 637.65, and the weight of the ice downward negative. The sum should be 0 for static equilibrium, balance. So in that case, we can transpose. Remember, we don't know what is the buoyant force, how much is the buoyant force, and what is the weight of the ice. We only know the weight of the woman. So algebra, transpose that to the right side, okay? Or remember that the buoyant force is, in our Archimedes principle, is rho gv, that volume of the weight of the fluid displaced. Okay, the buoyant force is the weight of the fluid displaced. What is the displaced fluid? The displaced fluid is water. So the ice submerged, then the displaced fluid is also a water. But we cannot observe that in the surface, the increase of the level. Why? Because it is a large, no? It is assumed to be a large container. So therefore, we cannot notice the increase of height due to the submersion of ice. Okay, but take note, buoyant force is the weight of the fluid displaced. And the weight of the fluid displaced is the density of the fluid, which is water, times the acceleration due to gravity, times the volume displaced. Okay? The occupied space of the ice is actually the volume displaced. Then subtracted by the weight of the woman, then minus the weight of the ice. Again, we learn that the weight of any particle substance is rho gv. Okay, so in this case, we will use the rho gv to remove the weight of the ice, because we don't know the weight of the ice. But we have the density of ice in our table, no? In our previous topic in density. We have the density of ice. Then we have the acceleration due to gravity, but we don't know the volume of ice. So when you look at the equation, we have two unknowns. We have the weight of the ice, and we have the volume, the volume of the ice and the volume displaced. But remember that the volume displaced is the same as the volume of the ice. Meaning, we can replace the volume displaced by the volume of ice. So in that case, we have only one unknown. Densities are known, we have the table. So in that case, we can solve for the volume of the ice. So again, transpose the positive to the right, which is, then we have that result. And the volume of ice is common, so we can take it out. Okay, then we can solve it. But before that, we need the what? Okay, so So apply simple algebra, okay? Then transpose, okay? Can you remove the negative sign? So we have what? Take the common factor volume-wise. So we have rho g minus rho ice times g. So the common factor is volume of ice and the density, gravitation acceleration. So then after that, divide both sides by the density times the quantity, the rho density of water minus density of ice. Then we have that. Now using the table, remember that the density of water is 1000, so replace it, and the density of ice is 0.92 times 10 raised to 3 for the ice. Then substitute everything. G is 9.81, then calculate, and the answer is 0.82 cubic meter. That is the volume of the ice. Okay, this is the answer to the problem. We are able to solve for the volume of ice, and that is because of the Archimedes principle. Any body immersed in a fluid is always subjected by a buoyant force. Then that buoyant force, which is in upward direction, is equivalent to the fluid displaced. And with the principle of Newton, in the first law of Newton, static equilibrium, combination of the two principles will lead us to calculate the volume of the ice. That's it. Okay. So next question. Okay. Now the problem says that we have the rock that has a mass of 1.8 kilogram mass. Okay. We have the rock, and when it is suspended from the when the rock is suspended from the lower end of a string, so we have the string, and totally submerged in the water, the tension in the string is 12.8 newtons. The question is, what is the smallest density of the liquid in which the rock will float? Okay? Meaning that data, the 12.8 is the tension of the string when the rock is on the water. But the question is, what is the density? Meaning, other than water, what is now the density based on that information that the rock will float? Meaning, without the support of the string. Remember, it's difficult to visualize how to allow the rock to float into the liquid. So surely the rock will not float into the water. So all you need to do is to increase the density. Is it possible that the rock will float? Let's see. Theoretically, no? Although it's difficult to visualize, but the theory can provide the answer. Okay, so we have the rock and it was submerged into the water. The water, remember, is 1000 kilograms. It is fully submerged according to the problem. And the weight of the rock is 1.8 kilograms. And the string, no? The tension in the string, meaning it is the weight of the rock in air, it is 12.8 newtons. So we have two forces on that. No? We have the water is 1000 kilogram per cubic meter. That's the density of water because it was submerged into the water. Okay, so the weight of the rock, remember, is downward, just like what we did in the previous problem, because the weight is always downward. This is negative. Okay, then upward, which is the reading in the tension, which is 12.8 newtons, and that is upward. Okay, why? Because remember, the string cannot hold compression. All you need to do for the string is to apply a tensile force. So it applies a tensile force away from the stone. So it should be upward, meaning it is positive. Okay? And aside from that forces we indicated, because the stone is submerged, completely submerged into the water, or remember, partially or completely, it experiences what? A buoyant force. The buoyant force is always upward. Take note, the buoyant force is always upward, meaning it's positive. Okay, with this information, remember that, what's the question? What is the smallest density in the liquid? So this is not yet the problem. This is, the data are given based on the stone submerged into the water. But with this, we can solve for, remember that we can solve, because rock is 1.8 kilogram force. Convert that to Newton and for consistency, then we can solve for the buoyant force. And that buoyant force is only for the stone submerged into the water. But remember that the volume of the stone now, using the amount of the buoyant force, can be computed, because take note that the weight of the stone is rho gv. Meaning, with this data, given information, we can solve for the volume of the stone, and that volume stone can be used for another submersion, and let us say liquid. So this is now the question, what is the smallest density that the rock will float? Because the rock will normally submerge into the water. So without the support of the string, the rock will continue to move downward until it will balance for some pressures. So as the rock continues to move downward, it increases its pressure until such time that it was being normalized. Okay? For a distance below. Okay, so let's do it. No? So the weight should be converted into Newton, or the mass should be converted into Newton in order to provide the weight of the rock. So simply multiply 9.81, then the answer is 17.66 Newton. As I've said, in air, the buoyant force is negligible, so nothing to worry. Just convert it to Newton. Okay, so then we already know that the force of the weight of the stone is downward, and that is 17.6 negative. Okay, so summing up all forces, again, apply the Newton's law, should be 0. So we have 3 forces, positive buoyant force, and the 12.8, and we have the 17.66 downward minus. Then equate to 0. So again, we can solve for the buoyant force, and the buoyant force is simply as 5.92 in that case. Meaning the buoyant force is 5.92 when the stone is on the submerged on the water. Okay? Now, but remember that the buoyant force is rho gv, the density of water, times what? The acceleration times the displaced volume. We don't know the displaced volume, but we have the buoyant force. In other words, we can compute for the displaced. Okay? We can compute for the displaced volume. Water is 1,000, 9.8 is acceleration due to gravity, and the volume displaced is unknown and equivalent to 5.92. Solve for the displaced, and the answer is 0.006 cubic meter. That is the volume of the displaced water. Take note, displaced water. So, meaning the volume displaced water is the same as the volume of the rock. Okay, take note of that. The volume displaced fluid is the same as the volume of the submerged particle. In this case, the rock. So it's very useful to have this value, because when we transfer this object to another fluid, we can utilize the volume of the rock. Okay, so take note of that the volume of the rock is 0.006 cubic meter. Okay, so here comes another fluid. This is no longer water. So we don't know the liquid. And this is the question. What is the smallest density of this liquid other than water? Because the data shows that the rock should be submerged completely. Now, without the support, then the rock will move down into the water. Now, we are challenged to this problem. What should be the density of the liquid in order to the rock to float completely? Okay, to float into the liquid. So, the smallest density, because if you increase the density beyond the smallest, then it will float, no, partially. But that one is completely submerged. So it should be the minimum density, the smallest density. So how will you deal with this problem? So notice that there are only two forces on that case. Unlike before in water, there are three. Why? Because there is a tension in the cord, in the string. The weight is still the same, 17.66. And the buoyant force this is not the buoyant force we calculated before. Because that buoyant force is intended for water only. This buoyant force is the buoyant force due to the unknown density liquid. We don't know what is the density of that, but we are looking for that answer. So how will you solve this problem? Okay, simply use the same principle. No? We apply the Archimedes principle by solving buoyant force, then apply the Newton's law, the first law of Newton, the static equilibrium. Now in this case, we have only two forces. So apply, summing up all forces along y. So the buoyant force 2, which is the buoyant force in a non-liquid, subtracted with the weight downward, the sum should be 0. So then, buoyant force is just equal to 17.66 newtons. Okay? Now what is buoyant force? Using the principle of Archimedes, it is rho g v. Meaning the density, which is unknown, we don't know the answer. The acceleration due to gravity is given, constant. And the volume of the rock. Remember, the volume of the rock was already computed in our previous calculations. It is 0.00306 cubic meter. So replace that value, okay? The density of liquid, acceleration due to gravity, the volume displaced, or the volume of the rock. Remember, they are the same. Then equate to 17.66. So the only unknown is only the the density of the liquid. So okay, so the volume displaced again is the same as the volume of the rock. So we just change it to rock because we are looking for, because our given is the rock, but they are the same, diba? So then compute for the density of liquid, a non-liquid. Then the answer says that it is 3,000 kilograms per cubic meter. Okay, analyze the result. Is this possible that the stone will float into the liquid? Yes, theoretically says the stone will float for a liquid that has a density of 3,000 kilogram per cubic meter. Okay. Now take note that, do we have the liquid that has this density? Would it be possible to have it? Remember that the density of aluminum is 2.7 times 10 raised to 3, or 2,700. That's the density of aluminum. Here comes the liquid. The theory says the density of liquid should be 3,000 cubic meter per kilogram per cubic meter in order to float for the rock. Okay? So, meaning for common liquids that we encountered, it is impossible that the rock will float. But remember that we have the liquid metal. Mercury is a liquid metal, and it is 13.6. Meaning 13,600 cubic meters. So meaning the stone will surely float into the liquid metal. Okay, in this case. So these are the answers to the problem. The density of a non-liquid. This is the density where the stone will float. The minimum density, meaning greater than this, it will move upward until it will float totally. But this is the minimum, because this will happen without the support of the tension of the cord, meaning you can ignore the tension, and that will be the minimum density. Lower than 3,000 it will submerge, but greater it will float. So this will be the minimum density of liquid. Okay, so try this. No, this is a good problem. A rock with a density of 1,200 kilograms per cubic meter is suspended from the lower end of the light string. When the rock is in air, the tension of the string is 28. newtons. What is the tension in the string when the rock is totally immersed in a liquid whose density is 750 kilograms per cubic meter? This is actually almost the same. No? All you need to do is to use the given, just like what we did. So in air, okay, then use the given, then construct the free body diagram, identify all the forces, then remember that the buoyant force is rho g v. Okay, so these are the answers. So again, the buoyant force will explain why the object floats. So in order to float the rock in our last problem, we need to have the greater amount of buoyant force in order to push it up. So why the object floats? Because of its density. Density can explain, and also the specific gravity. The buoyant force also will help us to explain why object floats, and it's because of density. The ship will float because it has a greater volume displaced, means the greater amount of buoyant force. Okay, so thank you for listening. See you on my next video.